Okay, thank you very much for introduction. Thank you very much for coming here. This talk will be about memory forensics, and in particular, how we propose a more principled approach for the assessment and design of memory forensic techniques. Despite being only 15 years old, memory forensic is nowadays used in many different scenarios, in many different contexts. It's used for malware analysis, in incident response activities, but also for the analysis of seized device. In all these three cases, the workflow of memory forensics is pretty similar. First of all, the analyst has to acquire a memory dump from the machine under analysis, so basically to read the content of the volatile memory. After he does so, he can run a bunch of different analyses on this memory dump, which we'll talk about later. And from this analysis, he gains evidence. So he understands basically what went wrong, what was the malware behavior, and so forth and so on. The focus of today's talk is going to be on the analysis part of memory forensics. Why analyses are important? Because analyses are the core of this discipline. With analysis, we can extract many different information from a memory dump. We can extract, for example, the list of processes, the list of kernel modules, and then given a process, we can tell which files this process had opened when the dump was taken. We can see which were the process memory mappings, if he had some sockets or some open connections, and so forth and so on. And moreover, we can also extract a bunch of other interesting system information. For example, the routine table, the kernel logs, the clipboard content. There is really many interesting stuff that we can extract from a memory dump. Just to give you a bit more context, Volatility, which is one of the most used framework for memory forensics out there, nowadays counts more than 100 plugins only for Windows. Plus, there is also a bunch of other plugins which are developed by the community, which is very active. But let's take a closer look on how this plugin works. For example, let's take the case when we ask Volatility to list the processes in a Linux memory dump. The first thing that the framework does is to locate the kernel global variable init task, which is of type taskstruct, which you might know taskstruct is a very important concept in the kernel because from there you can reach many other information that belongs to a process. Anyway, once the framework locates this variable, he simply dereferences the task field, and thus is reaching the second task. And then this process is simply repeated over and over again, up until the whole list of processes is reconstructed. But this is not the only way that the framework has to reconstruct the list of processes. There is another plugin, which is called Linux p-table, which, as the name suggests, uses the p-table of the kernel, which actually the kernel itself uses to locate a task given a PID. And also in this case, the modus operandi of the framework is very similar. So first of all, there is a global variable which is located, p- in this case, and then a bunch of pointers are dereferenced, a bunch of structures are traversed, and then the full list of processes is reconstructed. So let's get to the point. What's the problem with this approach to memory forensics? The problem is that these analyses are manually created, extracted, and implemented by humans nowadays. And this leaves many interesting questions open, which we are not able to answer. The first question, which is, I think, very interesting, is if there are other techniques to list processes under Linux. This is very important because you might know that malware authors can remove processes from the process list, and they're able to hide it from memory forensic techniques. And actually, I would expect that because the Linux kernel 4.19 nowadays contains more than 6,000 structures, which counts more than 40,000 fields. So it's really a huge graph of interconnected structures. But what's more interesting is if we can find a way to compare different techniques. It's unclear if there is a technique which is better than another, and for now we don't have an answer to this question. To answer this question, so we made this following contribution. First of all, we build a graph of kernel structures, which basically means in which nodes represent a kernel structure, an instance of a kernel structure, and an edge represent a pointer from one structure to another. Then we define a set of metrics which we report on our graph and which we use to evaluate forensic analysis. And finally, we combine these two contributions together and we study analysis by representing them, by expressing them as a path on our graph. But let's take a closer look on how we created this kernel graph. Actually, the algorithm is pretty simple. It's based on a work list, which gets initialized with the address of the kernel global variables. And then basically, we just iterate over this work list. So we take one structure, and we explore the structure, which means that we basically look at these fields, and if these fields are pointer to the structure, we reference them. If there are arrays, we just work the arrays. And this exploration will bring us to new structures, which are in turn appended to the work list. And then simply we repeat this process over again up until the work list is not empty. There is many challenges that came up when we try to implement this algorithm. They are all studied, and you can find them in the paper. But I'm pretty sure the most interesting one is the one related on the way that the kernel implements linked list, red-black trees, and other data structure. What is actually a problem? We can understand it from an example. So this is the way the kernel uses to implement a double linked list. And here the important thing to notice is that the task field doesn't point to the beginning of the next task, but instead it points in the middle of it. And the problem is that not all the fields point to their same own. For example, the children field doesn't point to children, but instead it points to siblings. And this is information that we need to have before we start the exploration, because if you assume that every field points to its own, then we will just make a wrong cast, and so we will just reach basically a wrong structure at the wrong offset. To solve this problem, we created the CLang plugin that analyzes the kernel abstract syntax tree. And what this plugin does is basically it intercepts all the function related to list management, in this case list add, and then basically it analyzes the argument to this function. So from this analysis, it is able to derive this set of rules. We were finally able to create our graph, which you can see in this slide, and which in our experiment contained around 100,000 structures, which are represented as nodes in the graph, and more than 800,000 pointers, which are instead represented as edges in the graph. So at this point, we start to look around for some metrics that we want to express on our graph. And the rationale behind these metrics is that they should capture different aspects of memory forensics. The first interesting aspect that we want to capture is the fact that nowadays memory is not acquired in an atomic way. What does this mean? This means that while the memory acquisition process is running, the operating system is not frozen. Because, for example, the memory acquisition process is nowadays implemented by a kernel driver. And this can actually introduce inconsistencies, because the resulting memory dump doesn't reflect the state of the memory at the given point in time, but instead is more like a mix of different time points. The second problem aspect of memory forensic is the fact that the layout of kernel structure changes across different kernel versions. Because fields are continuously added and removed from the definition of these structures, but also the very same kernel version compiled with a different configuration can result in a different layout. And moreover, another thing that we want to try to express on our graph is the fact that attackers can modify kernel structures. So it would be, for sure, pretty cool to be able to find some way to reach, for example, the tasks that pass by edges which are not tamperable by an attacker. So in this paper, we propose 5 different metrics. In this presentation, I will just talk about the first 3, but you can find all details in the paper. The first metric that we express on our graph is atomicity, which measures the distance in memory between 2 connected structures. To calculate this metric, what we did is that we mark the nodes with the physical address where the structure was residing in the physical memory, and on the edges, instead, we put the absolute distance between 2 connected structures. The second metric that we express on our graph is stability. That basically measures how long an edge remains stable in a running machine. And to do so, we took 25 different snapshots of the same virtual machine. So we created 25 different graphs. And then by looking at the edges in these graphs, we were able to understand which edges remain stable and which instead changed and when they changed. And finally, in this paper, we also show that metrics can be combined. For example, consistency is a combination of atomicity and stability, and this metric expresses the fact that an edge might be inconsistent because the memory is not acquired atomically. We use our framework in different scenarios. The first one that I will present today is the evaluation and the study of current memory forensic analysis. To study this analysis, what we did is that we took 17 different volatility plugins, from the plugin that lists the process, to the one that lists the ARP cache, to the one that lists the mount list, and we reported them to inside our graph. So we expressed them as a path on our graph. And the first interesting result came up when we start to look at the nodes which are used by these plugins. Because we found out that the 96% of these nodes belong to a giant, strongly connected component inside our graph, which contains on average the 53% of the total nodes. And this is a really interesting result, because this means that even if you're missing the entry points inside these connected components, so even if you're missing the position of the kernel global variable, just by finding one node which belongs to this component, then you're able to reach all the nodes used by this analysis. On the other hand, when we start to look at stability, we found out that 3 paths, so 3 analyses, never change in over 3 hours, so all across our experiment. On the other hand, we found out that 11 paths change in less than 1 minute, which actually hints the fact that the graph of kernel structure is not really stable, but instead changes quite a lot. But the most interesting result, for sure, came when we start to look at the consistency of these plugins. And in this case, we found out that depending on the speed of acquisition, 5 to 7 plugins are inconsistent. And here, of course, the result of the inconsistency, it really depends to which edge is inconsistent. If the edge is let's say, at the very beginning of this analysis, then the plugin might not return any output. But it can also happen that the plugin reports some wrong output. And finally, we also use our framework to try to find new ways to list processes. Actually, this was a problem which was much harder than expected, because, first of all, only when we started considering the shortest path from every root node to every task tract, we already find hundreds of millions of paths. So we run pretty soon in a path explosion problem. And the second problem is that not really every path inside our graph represents heuristics, because heuristics must be generated by an algorithm. So first of all, we focus on the problem of the path explosion problem, sorry. And to limit it, we removed every root node that is not connected to every task tract. Then we also removed all the edges which are used by known techniques, for example, the task field. We also remove all the similar edges, which are parallel edges, which basically have the same weight. And finally, to express the fact that an heuristic must be generated by an algorithm, we merge similar paths inside the templates. These templates are basically generated by keeping only the structure type of the node involved in a path, and then by squeezing together adjacent same type nodes. And with this approach, we were able to find 4,000 path templates, out of which we were able to find new interesting ways to list the processes. For sure, the first one is the most interesting one, which is in the C group category. And with these new heuristics, by passing through some C group structures, we are able to reach all the processes and all the threads which were running in the system. On the other hand, we also find 2 new techniques in the memory and file system category, which, by passing through memory or file system structures, are able to reach all the processes which have at least one memory mapped file. And finally, we also find a new way to list the kernel workers, which are still part of the process list. We implemented all of these new techniques as volatility plugins. So just to wrap it up, I hope I was able to convince you that forensic analysis can be and should be extracted and evaluated in a more principled way. To do so, what we did is that we created a kernel graph that model kernel structure, so that model how these structures are connected. We also define and propose a set of metrics that captures different aspects of memory forensics. And finally, we show that our framework can be used to study current and future memory forensic techniques. So I really think that there is more research that can be done with this framework. So we are releasing all the tool, all the source code, and all the artifacts that were produced during this work at this address. OK, sorry if I went a little bit too fast. Thank you very much for your attention. If you have any questions, I will be happy to take them.
We still have a bit of time for questions. Come on, I know nothing about memory forensics.
Yeah.
But I do have a question.
Yeah.
OK, so you have that whole list. Yeah, this is a great list. And to me, like manually, this kind of makes sense. If I want to list files like LSOF, great, right? File descriptors. How does your gigantic graph lead to like something that I can understand? Right. So like you went to like, OK, we can figure out like a way to get like list of PIDs. But like presumably there's other things that I'd care about. Like how do I use this tool?
Well, this tool can be, I mean, we have many other scenarios in which this tool can be used for sure, other than the two that I present in this presentation. I think, yeah, there is still a lot of work done that needs to be done in the exploration of this graph. So there is still many properties which are interesting for forensic that can be extracted.
I see. All right. Thanks.
Thank you very much.